Hey guys, I had a customer ask me for if it's possible to integrate an AiM MXg into a Racepak Smartwire system. So as you can see, I got the Smartwire system here. I have a CAN analyzer, which I'm going to be using for transmitting the messages. I use the CAN output on the AiM MXGs, or the AiM CAN outputs all the time, so I know that they're reliable and work. So we're not going to be testing with that, just to keep the amount of things that I have to manage as small as possible. So just a quick overview. We got the Smartwire set up from Racepak. We have a switching mechanism. It's like a membrane keypad that you have here. Seems to be working. And then we have their VNet. The VNet that we have is, it looks to be like adult Legos, I guess is the easiest way I can explain it. All I've done so far is I have taken my power supply, hooked it up to the battery input pin, and then or the battery input post, and I grabbed the ground from the from the headers. So now the system's on. It's plugged in via my mini USB cable, so mini USB to USB, and then he has now I have a Racepak Universal EFI CAN interface. So this thing right here is going to be required for something like this. The VNet is not very flexible. You need an external device to make any additional info that, like, to grab not AEN or not Racepak specific stuff. So it's just like this universal CAN adapter is what it looks like. So I have that basically connected via CAN high and CAN low. It's only got 2 wires on there. It's pretty straightforward install. So what I've done, funny enough, I actually was doing this for the first 8 or 9 minutes, and the video camera wasn't even recording. So I've already got a head start on you guys, but we'll go over some of the things that I did initially. First thing I did was, with everything connected, I read from the ECU. So we pulled this read right here, and it pulled up this 35 things that it needed to read. The process took maybe 2 minutes, maybe 1.5 minutes. Quite long. Once it did that, it populated here, but I only had ECU type. So I right-clicked on the ECU type, and I defined it as a user configurable. So they have a list of predefined ECU types, and the list is shockingly small, but we can work with it because it has a user-defined section. So what we're going to try to do is figure out how to make that user-defined input. Now the hard thing to get used to is everything's right-click based except for these buttons, and you have to send the configuration every time. So it sends it and it tells you that everything's good, and then once you make a big change like ECU type, you have to reread the information. So once I did that, it gave me this EFI setup option. So then I right-clicked on the EFI setup option, and I assigned the number of channels here. I want roughly 10 channels, maybe 15, but it should be easy to edit in the future. And then I set the CAN bus bitrate to 500K. And the reason I chose 500K is because the application that this is going into is I thought the button was on. The application it's going into is a CAN AiM, and the CAN AiM bus speed, since I'm sharing the CAN bus, is 500K. So this was predefined for me, but some of the options that you have are 1 megabit, 250K, 125, and so the most common. For this, we're going to choose 500K, and then I want my CAN bus terminating resistor on because I plan to connect it to another device, and that has a software selectable resistor, so I'll be able to, if I need to, enable and disable that. I'm not concerned with any of the transmit messages right now. So then we send this configuration, sends it to it, we hit OK, and then I have to do another full read. Once I did that, another 2 minutes of just waiting, the ECU CAN channels became available. So right now we're in uncharted waters. Neither of us have, neither me, myself, or you have been to this section. So we're going to right-click on the first channel, and it looks like we have an option to put a name. We're going to define this as water temp. Maybe we can do the full letter. Okay, so they have enough characters. So water temperature, VNet ID. I don't think we'll have to be managing this at all. Let's see what the options are. Yeah, this is going to be something internal to their VNet protocol, which I don't want to mess with in the slightest. So keep that the same. Specified linear conversion. This to me looks like a 4-step gain. So if you wanted to change the value, you would alter it here. So what this is saying is raw data value A, which is 0, will become 0, and raw data value B, which is 1, will become 1. That is a 1-to-1 conversion. It effectively makes no change, like multiplying by 1. Now, if we wanted to maybe double the value, I would probably put raw data value B, 0 is 0, and then raw data value B I would put at 1 and will become 2. That would give us a ×2 application. If I wanted to reverse it, I would probably do 2 in the value B and then will become 1, and that would cut it in half. And you can kind of play around with different gains and things like that to mess around with this. But for this, I just want to send whole numbers. I'm not concerned with decimal places. I just want simple control. Minimum result value, 0 to 10,000. I don't know why it chose that, but it did. In this application, we certainly don't need that, but we'll leave it as is. Display 3 digits before the decimal point. Since we're working with water temperature, if we get above 999 degrees Fahrenheit, we're going to have a problem, and it's not going to be the PDM's fault, so we'll leave it there. Resulting units, I intend to send it out as Fahrenheit, so we'll send it out as Fahrenheit. Smooth depth points. I don't know what that is. We're going to keep it as standard. So let's get into the nitty-gritty. So logger sample rate. This is defined in hertz. So we're getting 20 data points per second on the receive. The MXG can output at 100 times a second, and the ECU can output, I think we're probably storing that at maybe 10 times a second on the ECU. So we don't need to worry too much. 20 hertz, we can match that. CAN ID for message on the network. Now this is to edit the arbitration field, and for this I want to do a 29-bit message because the ECU reports 11-bit messages. So to not have any conflict, because we're sharing the same bus, I'm going to add a very long 29-bit message, and it's going to be, we'll keep it simple. We'll do, let's see, 100,000. So 100,000, and then I will just increment them in steps of 1 for the arbitration messages if I need it. CAN ID message type. Enter as follows. CAN ID message type, we are switching to 29-bit. I am a sucker for Big Endian. It's just my personal favorite. Little Endian, in my opinion, kind of sucks. It's hard to read on CAN analyzers. It's a nightmare. I don't like working with it, but it's not Big Endian for my choice. Let's see, message index byte location. So if the CAN messages use a byte to identify the message type, select byte 0 through 7, otherwise select none. So this would be like a row count. And the row count would be if you needed to maybe output 14 or 24 bytes of information on the same CAN ID, you would have a message index or a row count, a multiplexed message, and that would stream the same CAN ID, and it would have a secondary identifier that must be met to process the following data. Since we don't really need to use it, I'm not going to go into it much further, but maybe if you guys are interested in something like that, it's like a whole topic into itself. Let's see. So this is set to none. It's funny, it's a value of 255. We'll get into that later. Message index byte value. If the message index byte value location is enabled, enter the index value. Oh, so this would be the value that you expect to see for this CAN message with this index. So what's your row count number? We're not using it, so it doesn't matter. Message data byte containing low byte of data. Select the byte in the CAN message 0 base, which contains low bits of the data. So we have, I would assume, up until 7, right? So this is our first message. It is the first payload data following arbitration ID 100 or 100,000, and it's going to be 0. We're just going to start on the left-hand side and work our way all the way to the right. So we'll start with 0 and go go to 7. And if we need another CAN ID, we'll do it then. Message data byte containing the low byte of data, we just did that. Bit offset into first byte of data. So this is kind of cool. You can actually set a, you can't do it by much, but so you can only do the first byte of info. So let's say you had 13 messages or 13 bits of information, but you had the first couple were omitted and they're for something that you're not concerned with. It would be here, but we're not going to do that at all. So we'll set the bit offset. Data type is unsigned. So basically we can do an unsigned or a signed, and the unsigned is going to be from 0 to 255, or from 0 to I don't know, 1 byte, 2 byte, 65,535. Signed gives us an option to basically make a provision in the data for negative value. So instead of having 0 to 65,535 for a 2 byte message format, we can do 0. The calculated 0 is 32,600. It's basically half of 65,535. And that will be our 0, and anything below that value will be negative numbers. So -0, -1 will all count down to 0, true 0, and then everything above it will be counted as a positive integer. Now, 2 bytes of information, we can do that. I don't expect the water to ever be below 0 degrees Fahrenheit. So we are going to use unsigned in this application. Let's just see what else they have here. Single float and F24.8. Super uncommon. Well, unsigned is good for now. Number of bits in data received. So this is where we define the payload of information. Now, this is quite crucial because if you do too small of a payload, then you're going to truncate your information. You're not going to get everything you want, so it'll just cap out. So if we use, for example, 1 byte of information, let's see, does it start at 0? Or yeah, so if we use 1 byte of information, 8 bits, then the maximum value that we could expect to see is 255. Now for water temp, that's probably fine, 0 to 255. But for exhaust gas temperature, or maybe you were looking at fuel pressure and kPa, like you're gonna outscale it, you're gonna outgrow it. So best thing to do would be to, if you're unsure, go to a two byte format. A 2 byte, so one byte of information is 255 unique positions, 256, 0 to 255. And then a 2 byte payload is 0 to 65,535. And I've been saying that word, or that number, quite a bit, but let's just double check to make sure that that is actually the right. So we'll just do this scientific. The way you calculate it is just, it's exponential, so it's 2 to the power of the number of bits that you have. 65,535, because you have a 0, that is a numeric value that counts. So there's 65,536 different options in 2 bytes of info. Plenty of information, especially if you wanted to send a decimal point. That would be the way to do it, because then we could send a value of 655 with 2 decimal places of precision, and that would be, acceptable for many things. You could probably send EGT numbers with 1 decimal place of precision. So 2 bytes of information is always a safe bet. So we're going to go ahead and just keep it like that. And I think we've pretty much gone through everything. So we're just going to send this configuration over. And okay. Now what we'll do is we'll try to do something with it. Oh, you see, it didn't actually, ECU channel 1, ECU chan 2, like it didn't, I don't see the difference here, so I have to reread this, and this is just problematic. Save changes to the Smartwire configuration. No, because I'm a rebel. So now it's going to go through a whole nother process, and I talked about this earlier, but this is like the 3rd time that I've actually had to reread, and there may be something simple that I'm missing, like a refresh option, but I just don't use the software enough to know for sure. And I know that this works, so we're just gonna wait. Okay, device is read successful. Now we can go in and This is still not changed. But it does have most of the information. Did I not? Okay, I guess maybe it just didn't take the name. So maybe I didn't need to do that read. Let's see. First thing to do is to test what we've done. So to do this, I'm going to look at taking the first output that I have and maybe setting the on conditions for it. This seems to be good. Perfect. So we got water temperature, operation greater than, true condition 100, false condition 90. So, I mean, I guess it would, I want it to be 190 and 170. And what I'm hoping is that this water temperature greater than 190, it activates, and then it won't deactivate until the value becomes below 170. So then I have to right click. Oh, whoops. So looks like it had some base configuration stuff in there. So now place cursor inside the box, right click to add or remove condition. So we'll just right click and add this water temperature. And I like that they have this logic like or. So if I had a couple other things that I wanted to have controlled by the output of channel 1, I could actually do all of them right here. And it looks like I have 10 different things that I could have activate this output. And I wonder if they have any and condition, and or. Okay, so that's a nice feature. So a true delay and a false delay. If I wanted it to hold for a certain period of time, I could see this for maybe like a sump activation, something like that, where I'm not super concerned with like the small chatter, especially when getting airborne. I don't want it like kicking on and kicking off, kicking on and kicking off. I would put a true delay on there, so it would have to be true for an extended period of time before I activated this control, and the same with the false condition. So that's cool. So we'll send this I don't think I have to. So let's see, fuse current. I could set this here to whatever amperage I wanted to. Since this is a fan, I would think that 20 amps. We'll probably bump this to 25. Depending on how big the fan was and how much current it demanded, this is where we would set our fuse protection. Graph minimum and maximum is probably for the telemetry side of things. Volts graph min, volts graph max. I'm not super fuse reset delay. So it's set to 1 second, and the max fuse retries is 100. That seems excessive. So it's going to try over the next 100 seconds to turn the fan back on. So maybe if it cools down or something like that. But I don't really want that. So we're going to set this to like 5. And it's funny, you notice 65,535, the other 255. You start seeing these numbers everywhere. VNet, I'm not going to mess with. Output function, constant on. Let's see, what do we have? Flash, latch, single pulse. So that's pretty cool. We'll stick with constant on for now. Logger sample rate disabled. Update rate, switch bus update rate, on delay time, off delay time. All right, so let's send this. Okay, so we'll start the live channel data, and you notice that it's off right now. So what I have going in the background, and I'll just give you a quick little view because this is something I use all the time. This is my vehicle spy. This is my CAN analyzer here, and it allows me to basically fake whatever CAN message systems I want. I also use it for a lot of ECU development and things like that. It's a very, very powerful tool, very costly. So what I would normally keep this up here and show you guys all about it, but it has nothing to do with, we're just simulating an MXG right now. So I will switch over to this. We'll go online with it. All right, folks, and there we have it. We have, as I roll my values here, let me make my false condition here. The status is set to off. I will set my value at 190 right now, still set to off because our condition is set to greater than 190. As I increment up to 191, the status goes on. I will reduce the value until I get below 170. 75, 74, 73, 72, 71, 70, 69. There we go. And it is now off. So that is an easy way to output or to use a power distribution module, and it keeps the wiring to a minimum. So we're able to process the ECU data and send it to the Smartwire device so that it can manipulate the power control for the rest of the vehicle. We've done this with 4 wires, power, ground, CAN high, and CAN low. So definitely a step above. And the nice thing is you can set your fuses. I mean, it streamlines your wiring significantly. So we'll just go over a quick recap, because maybe we'll just use the recap for all of the info for the video, because this is already 40 minutes long. Quick recap. We go to ECU type, set it to user configured, send the transmission, read it from the hardware. Wait, EFI setup, go to number of channels. We want to output 10 channels of information. Set the bus rate to what is appropriate for our settings. In this application, it's 500K. Set the terminating resistor to the on. That is really up to you. If you have external resistors, it's something that you'll have to manage. Easily testable. So the CAN bus with everything connected and powered on should have a nice 60 ohms of resistance between CAN high and CAN low. And you get that by having a terminating resistor in one device and a terminating resistor in another device. 120 ohms at each side. Anything in between does not need a resistor value. So we send this to the hardware. I'm not concerned with transmitted messages. We send this over to it, send configuration, and then we can have our 10 channels of data to process. So set the sampling rate to 20 hertz, set the message at 100,000. In this case, I chose a 29-bit message so that there would be no conflict with the ECU that I plan to integrate it with as well. The extended message format, I set it to 29 bits to make sure that it had enough room for this 100,000. And then I set my Indian type to big. And then I set, these are basically set to off. We're not using any of these. They're row counting mechanisms. And then the message data byte, this kind of threw me for a loop, because it was it asked me to place the byte where the smallest incremented information would be. That's your 1 position, your 10 position, and I just don't understand the need for it. I've already assigned Big Indian and I have my bit offset here, but threw me for a loop. I had it set at 0, but it did need to be set to 1 in this case. So we're sending 2 bytes of information, byte 0 and byte 1 of CAN ID 100,000. And the low byte of data is byte 1, not byte 0. So switch that up, and now everything seems to be working as intended. The bit offset, since we're using byte 0 and byte 1, is set to 0, and it's a true 16-bit message, so we're sending it in a word format. So we're using whole bytes here. Let's not reinvent the wheel. Now that that's done, I went to my output control. I set my on condition for greater than 190, and then to turn off at 170. And I can go in and set my values. So as we can see, I'll pull this over to here. As we can see, as I go up to 190, we'll just do 191. Well, that should be on, shouldn't it? My hardware is not having fun today. I'm using a cheap USB-C controller and it's not working well for me. Okay. So let's try this again. We'll set this to, first we'll make sure that the hardware is off, so we'll send 160. validate that the hardware is off. Perfect. Now we will send our command value of 191, should enable the output status to on, and then we will check the off status by going to 170, and now the hardware's off. So everything is being interpreted correctly. Now we'll switch over to, now that, I mean, that's, you would just basically fill this ECU, these ECU channels here with the pertinent information that you want to control all of your outputs. So in that case, it's really just a rinse and repeat. Now we'll go to our hardware setup, and let's say I wanted to output this on CAN 1 or CAN 2, depending on what I have access to and what's required. The output's really simple. All we have to do is do a payload here, and then we have our ID in hex, and we just enter in our value of 100,000. The little cursor there. So we're outputting our CAN ID of 100,000. We go to Big Indian. I'll eventually use all 8 bytes, so I'm going to set that up, and the frequency will match at 20 hertz. I put that as OK, and I access my first 2 bytes of information. I set the number of bytes here, and I want to use a channel. So for this, we'll go from the ECU, we'll set the water temperature, and I'm going to send it with the same multiplier and offset. I didn't manage those in any special way, so that's a 1 and a 0. I hit OK. Now I'm outputting my data at 500K on CAN bus 1 for water temperature. When the value gets above 190, we will have a activation of the first power distribution channel, and then when it gets below 170, it will deactivate. And that's it, guys. That is a full installation. I mean, I know it's only one channel, but you would just extrapolate that out to almost anything that you could possibly want to do. Just make sure to manage the bus speed correctly. That's probably the biggest hiccup, is people not managing the bus speed. And then you have small things like the asking for the low byte. If it's in Big Indian, it is the furthest right byte on the byte map. So this would be the low byte of information. This is where your small digits are going to happen, your decimal places, your 1 position, your 10 position. And then this is where your large information. So if you think about the way a number is written, we read 100,000. The low byte would be here. The high byte would be here. And that's really it. If you guys have any questions or comments, let me know. This is my first video of helping. This is the stuff I do every single day. So if you like the content, let me know. If there's something that's very specific, give me some ideas what to make videos of, and I'll try to get them. If you like what you saw, go ahead and subscribe, and we'll hope to get more content for you.